Hi, this is Dan Bullard, retired electronics engineer. It's a beautiful day. My hair is going big time. Oh, terrible. I want to talk about a couple of things. Mostly idiots. I've worked with a lot of idiots. One was, and I've told you about some military people that I worked with. This was military. I did a test program for an analog switch. Now, an analog switch, like this one, it wasn't this one, but it was something like it. And so basically, treat it like a relay, okay? It's a switch. And, you know, this is like a 25 ohm one, but there's like, I've gotten MOSFETs down to 1,000th of an ohm, and I could make an analog switch out of that. So, you know, analog switches have very low impedance. And so I wrote this test program for this device, and it looked pretty obvious. And in their schematic that they wanted relays between the input and the output so that they could test on-state leakage. Now think about that, on-state leakage. The switch is on, and you're going to measure leakage. Now, we've measured we can measure off-state leakage very easily just by putting a VI on there, forcing a voltage, and then measuring the current. Off-state leakage, simple. On-state leakage, simple, because just leave one of the inputs open, and you don't have to worry about it. Now it's just basically both channels open. And they're only interconnected to each other, nothing else. And these guys wanted a relay to connect the input to the output. And I'm like, okay, in test, and I'll tell you this is the way test works. If I have something I have to test, and it relies on knowing something else, I'll test that something else first. So, for example, on-state leakage. If I can first turn and validate through test that the switch comes on, so basically I force a voltage and measure the current with the other side connected to some other load or VI or who knows what, I can measure the on-state resistance, and I know that those two are connected. So now I am free to go off and do an on-state leakage test, knowing that those two pins are connected. You got to be careful how you order these things. A buddy of mine, and I've talked about him before, a buddy of mine wrote a test program. He had a test program for a device. He finally got around to doing all the tests, and one of the tests was the iOS test. So I have to test output current in short circuit. So I basically have to connect the output to ground, and I have to make it drive high and then measure the current and make sure that it doesn't blow up, and make sure that it could do it if it has to. If it has to drive a short with a high coming out, it's not going to melt anything. Now, this test, it's not destructive, not necessarily, but you never know. And so what this guy did, he wrote this test, and then he ended up putting it at the end of the test program. At the end of the test program. And so now, if your iOS test was destructive, if it created a fault in the device, you've just created a fault, and you're not going to test it anymore, and you ship it to the customer, and the customer says, hey, hang on a minute, this device doesn't work. And you're like, well, I tested everything. Well, yeah, but just before you shipped it out, you blew it up. So yeah, so you have to know how things relate to each other. And so if I can test the on current through a device, so the analog switch, verify that the input and the output are connected together, then I don't need this stupid relay, because it just adds hardware, which, you know what that's going to do? That's going to mess up my input off-state leakage. the off-state leakage, because that other pin is now connected to that relay, and that relay could leak. The wiring, just for that function, could leak. And I want to keep, for leakage tests, I want to keep the number of other things connected to that pin to the minimum, and that's the way you should do it. And this is, this is just stuff we do in test, and I'm like, I'm buried in tests. That's what I do. And so you have to think about all those things, right? If you have some kind, if you have some kind of a timing test, don't leave a stub, 3 feet long, because it'll cause a reflection. And those reflections are very, very dangerous for your comparator. I mean, that can really mess you up, so you don't do that. And so the same is true for leakage tests. You don't leave extra things connected if you're going to do a leakage test. In fact, with some op amps, I've seen this, because I've talked about op amp leakage, and I've seen op amp fixtures done with Teflon, special Teflon PC boards, so that you could test the leakage of that input on that op amp to the nth friggin' degree. And it's really something to see. You see Teflon connectors and stuff. It's really nuts. But people make some huge mistakes. So these guys argued with me. These relays had to be in there. They had to be there. And it's like, why do they have to be there? So I told them I'm not doing it. I'm just not doing it. And they argued with me, and they thought that I was negligent in my duty because I didn't do that test. Well, I've already verified that I've got a relay from here to there, so what do I need another relay for other than to cause leakage? Forget it. In another case, I did a voltage to frequency converter. So it took a voltage or a current and then would translate that into a frequency. And so very low voltages would cause a very low frequency, and then higher voltages would cause a higher frequency. And this thing would oscillate. It was basically a free-running oscillator. It would oscillate from as low as like 10 hertz to 100 kilohertz. So now these guys wanted this thing tested. Now, how do you test something like that? They want to test for linearity. So how do you test something like that? Well, let's see, the lowest setting is 10 hertz, so probably that's like the bare minimum resolution. And so go 10 hertz at a time all the way to 100 kilohertz. Well, with a TMU, that's what you have to use to measure these things, or you can get fancy, but it takes time to measure time. And so if you're measuring 10 hertz, that takes, 100 milliseconds. Now, we're going to advance that every 10 hertz all the way up to 100 kilohertz. That's crazy. That is absolutely nuts. Now, this was an analog device, and so there's no need to assume that it's got some nonlinearity somewhere in there. It's just an analog device. And so what I did is, I want to save time. I do production tests. That's what I do. The test programs that I write go into testers that run hundreds, thousands, millions of semiconductor devices, hopefully before the thing craps out, runs out of memory, or the tester breaks, or who knows what. So we want to get through millions of devices, and so I want to get through this quick. So what I did was, I did it as an exponential curve. So from like 10 hertz to 20 hertz, I measured that, and then I boosted the voltage up so that it would go to like 33 hertz, and then boosted it up a little more so it would go up to 48 hertz, and then boosted it up so by the time I got to 100 kilohertz, I was doing like 10 kilohertz steps, and that didn't take that long at all. It really went fast, and these guys were outraged. How dare I not do a linear ramp to measure this thing? I'm like, what is wrong with you guys? It'll take days, days, because the TMU is pretty slow, So especially if you're doing 10 hertz resolution, it's very slow. So you got to do it. I mean, the TV tuner that I did for Maxim, that took, I think it was under 10 seconds. That was my goal, was to get it under 10 seconds. And I had to verify, it's a TV tuner, I had to verify every channel, everything. Like, can you get through your TV tuner? Can you get through all the channels in under 10 seconds? I don't think so. So that's the kind of stuff I've done. That's what I do. Automatic test. I don't go in there and measure things. I mean, I do if I have to, but generally I use a tester to do it all. And the tester is all programmed with C++ or C or Pascal back in the olden days. And you basically write a test program to go through and verify everything. You make sure that the test program doesn't spike the part or doesn't do anything. At Maxim, we had a requirement that when you took a program to production level, you had to go through with a scope on every pin and make sure you weren't spiking it. Well, the power pins was a big deal. Make sure you weren't spiking the power pins, because they actually had that happen. They had a customer complain that some of their devices were blown up. They didn't work at all. And so they looked at it and they figured out the test program was generating a spike on the power pin just at the end of test, just like that other case I mentioned. And so right at the end of test, you've tested the whole device, it passes, everything's good to go. You shut it down, and the moment you shut it down, you blow it up. And so this customer was complaining to Maxim. That's how this works, okay? The program tests a device at the maker site, probably tested twice, at wafer sort and then at final test when it's in a package. And then it goes to the customer, and the customer just, used to be they didn't assume, but now they can assume that anything that comes from the factory is good to go. So then they can solder it into a circuit board along with 50 other chips and hope to God that they all work. And if one of them doesn't, it costs that guy some money, because the circuit board, all the chips that he went on there, he's not going to get them back off. He's not going to desolder them. And so all that stuff gets thrown away. So that really costs them, even one chip costs them a lot of money. So they don't want that, as you can imagine. So that's how you do production test. Anyway, there are some stupid people out there. Be aware of that, and just be ready for them. You got to argue with them, and boy, I've done my share. Anyway, so once again from the river, this is Dan Bullard. See you later.